the quantum of water being allocated into different areas, different fields, different domains. One of the important was the domestic water allocation from the total water availability in India or across the world. And in developing and underdeveloped countries, we are having only say 5 to 6% of allocation for domestic water, whereas in the developed countries it is fairly more than 10% of the water allocation. And for that we need to create infrastructure, one thing. Second thing, we have to reduce our irrigation water utilization. We have to increase our efficiencies and so on, for industry and recreational and for shipping and navigation, we need to allocate the water. And we have to enhance, like we have done it from Varanasi to Kolkata. There is inland water transportation done in last few years. Like in last 4 or 5 years, this has been done, that cargo is being taken from northern India to eastern part of the country through the Ganga river. And many banks and the ghats and other things are being developed across the nation. Today, we are understanding the forces acting, which ultimately would lead to the understanding of the design of these gigantic hydraulic structures. They are larger than what we could perceive. Usually, the buildings, 10-story, 20-story, 50-story, 100 stories of building, they are larger. They consume large quantity of concrete, and forces acting on them is like many-fold compared to the residential and other buildings and transportation facilities in the civil engineering. So we have to understand the type of forces acting on these gravity dams. This here on the slide, there are mention of 9 forces which are possible. And there could be a few more depending upon the location of the dam. But mostly as per IS code 6512, which is there for the design of gravity dams, and the forces are mentioned and calculation for the same is mentioned in that IS code. Now the thing is that how should we go ahead with these forces? There are 9 forces mentioned and could be more than this, like weight of the dam, water pressure, which is onto the upstream and downstream side many a times, then the uplift pressure, wave pressure, earth and silt pressure, earthquake force or pressure, then ice pressure, wind pressure, thermal pressure, and depending upon the location, you could have one, two more in the list. So these forces are not like in equal quantum. We need to look at that, how these forces really influencing the design. So let's move to the out of 9. I would say that 1, 2, and 3 are the measure we need to consider, that major quantum of force exerted by these 3 criteria. That is, one is the weight of the dam, the second is the water which is being upheld onto the upstream side, and the uplift pressure. Then the next 2, wave pressure and earthquake pressure. While calculating the load combinations like we do in the residential and the commercial buildings, the load combination, here also the wave pressure and earth pressures are being considered for the load combinations, but first three are always taken into consideration, and rest of the forces like ice pressure, wind pressure, and thermal, they depending upon their location, geographical location, we need to consider. Like in the Himalaya region, if we are constructing dam in say Rohtang Pass or beyond that, then we have to go for the ice pressure, where temperatures fall down to sub-zero level. Wind pressures, if the dam is located in the coastal area and wind is blowing more than 80 kmph, then definitely we have to be very vigilant about this force. We consider this also in residential buildings. You consider it as force in 875, your IS code, that different loads acting on the buildings or the civil structures. So that is also there in this thermal loads. If the structure is located onto the equatorial fields and say in the southern part of country, then these forces, thermal forces, mainly the changes in temperature during day and night, which causes the expansion and contraction in the concrete, especially concrete joints, then we need to consider the thermal loads. The calculation of these loads is very simple if we focus upon the physics of the structure, physical dimensions of the structure. If we understand different component of the structure, then calculation is not that difficult. Only thing is that we have to have resilient while calculating the way we calculate these forces. Like the weight of the dam, I take the first the weight of them. This is how what I just mentioned you, that forces which are important and not important. There are two forces, two type of forces here mentioned. One is which we could calculable forces, and second we have to have kind of assumptions like earthquake forces. We only could assume, they are not visible, they only occur as a kind of surprise to us. So we have to have assumption that in which zone our location is and what is the frequency of occurring such earthquake tremors in particular area. So that kind of division in the forces can be done. The first force, which is only the stabilizing force, which is only the counterbalancing force to all the destabilizing forces in the gravity dams. So this weight of the dam, that's why the weight of the dam means G is included into G, and this G, because of that gravity, we are calling it as a gravity dam. Gravity is only the stabilizing force, and the unit weight of concrete generally taken as like 24 kilonewton per meter cube, or say 2400 kg per meter cube. Similarly, if you are going for a gravity dam of say masonry, then we may consider around 23 kilonewton. And if the brickwork is not that good, then ranging from 20 to 23 kilonewton per meter cube. This also should be taken as per 875, because unit weight are described for different type of masonry works into that IS code. But in general, if the work is not that bigger or detailed, we roughly for the sake of calculation in academics for your examination could consider 23 kilonewton per meter cube. So for that purpose, while calculating in examination, you can take these rough figures, that 24, 23. The actual in your this mid exam, I have asked that what is the shape of the basic shape of the gravity dam. It should be triangular. You have gone for trapezoidal, and this is a kind of practical shape. This is not a basic profile, the elementary profile of the dam. Profile of the dam is when it stops the water and when it holds the water, and when it holds the water, then water is being exerted by the water, and it is triangular in shape. The force is acting on the dam in triangular in shape. So your elementary shape of the dam would be a triangular, not a trapezoidal. If you have clicked the trapezoidal and likewise, so that is not correct answer. Now look at this. This is a practical shape. Practical shape means when we arrive considering different other forces, other requirements, like we are installing gate on the top, we are constructing road on the top of the dam, and we are also constructing inspection gallery, then we are constructing the sluices, then many other things are being added to the primary elementary section of the dam. So ultimately, when we economize the dam, then dam section comes out like this, say in this kind of, say, which is mostly a triangular, but there is additional concreting done upstream, like here, additional concreting done here for the road section, and then the equilibrium is achieved so that it should not like go and overturn or collapse or failure. To avoid failure, you can understand in simplistic words. So this is what the dam of the weight. So if it is the kind of shape we are going to construct, then the weight of the dam can be calculated like we could divide in this triangle here, then this rectangular and triangle W1, W2, W3. The calculation of weight is very simple. We take what? We take the cross-sectional area of the dam here, cross-sectional area of all three sections, and then add up, and then we multiply by the unit weight of this concrete material, say 2500 kg per meter cube. Why so? Only area is being multiplied because whenever we design a concrete dam or any dam, then we do the calculation per unit length of the dam. Say dam length is 900 meter. Then we are not going to design each and every section. We design first the critical section 1 meter only, and for that 1 meter of lamina that is designed right from the bottom foundation to the top of it. So this would clear the picture that how the design is done, that we design only 1 meter section, unit length of the dam. Dam as a whole, 1 kilometer long or 900 kilometer long is not designed. Only 1 meter unit length is designed, and we take this cross section of the dam and we design it. Then the joints are created, and we finally, when all the unit lengths are combined, say 900 laminas are combined, then the joints are taken care of at the end. So this is what is the engineering design required at initial stages, and later stages when we club all things, when we integrate all things, we take into consideration the kind of joining of different unit lengths. The second is the water pressure. Water is in the reservoir on upstream of the dam wall, and again we calculate the volume and we multiply by the unit weight. In unit weight, we take it 10 kilonewton per meter cube or 1000 kg per meter cube, not 9.81, because this is onto the safer side. There are lot many forces, so this is not going to create so much of the difference, and generally in dam design it is taken as 10 kilonewton per meter cube. This is how we calculate the water pressure. There are two things. One is the water pressure. Water pressure is exerted by the water itself, and uplift water which is seeping through the foundation as well as through the dam section. So you mind it that there are two kind of water forces. One is the water directly exerting the pressure onto the section. Second, seeping water through the foundation or through the dam, which exerts, and that is known as the uplift pressure. So uplift pressure is different than the water pressure, and water pressure is here. If you could look at my arrow, then this arrow would show you the this is triangular incept. So two kind of forces you could assume. If this is a kind of vertical phase, if there is not a slanting upstream, then this is a triangular. If there is a slant, then we have to consider this additional, which is colored gray and yellow here. You look at. So we have to have two types of water pressure being exerted onto the section, and this triangular, this whole water is exerting pressure here, and this which is being held onto the slant position is exerting downward. This is horizontal force by the water. This is vertical downward by the water onto the. So this is rather stabilizing, add to the weight of the weight to the whole section. So this need to be taken care of. Now, the simple hydrostatic force, as you know, that at any section, if you draw this hydrostatic force, then intensity is directly proportional to depth of water, and it increases downward. And at the bottom, it is total height. If h, then the intensity would be gamma wh. You could look at here. And at any section, at depth y, this intensity would be gamma wy. So that could be taken, and the total water force or water pressure being exerted, pH, which in the previous section here this is half of this base into the height. So gamma WH into the height into half, because that is what is the total sectional area, and you then multiply by the unit weight of the water, you will get the water pressure being exerted onto the, it acts, since it's a triangular section, it acts h by 3 from the bottom and 2/3 of h from the top of the dam up till where the water is being stored, say normal pool level or the maximum pool level. From there you need to calculate or measure the height. This is when face is inclined. I have already explained that the rectangular column add to the weight of the dam. So we generally add it to the weight of the dam. So that is the additional advantage of the slant position of the dam. Now this is the uplift pressure. The uplift pressure is, I already explained that uplift seeping water which is being stored onto upstream side keeps seeping through the dam. Even the concrete is not 100% watertight. There are pores in the concrete, there is pores in the say rocky foundation, and there are pores in the river bed. So water seeping will flow down, as we have seen in the weirs and barrages, and it exerts the uplift pressure onto the dam. The uplift pressure we have seen also into the weirs and barrages, and similarly we calculate the dam section. The important thing is that when the concrete is more porous, then we have to look into that every section, say dam is 100-meter height, then each 5-meter horizontal plane, we have to calculate that how much is the pore or this uplift pressure is there, because it actually counteracts the weight of the dam. So that is kind of shear failure could take place at any plane of the dam, ranging from say bottom 5 meter, then 10 meter, then 15 meter. So the horizontal plane, each and every plane at 5 meter, and for severity we could select a horizontal plane at every meter. So depending upon the importance and criticality of the structure, we go and measure, check the horizontal plane and forces acting for the shear failure of the dam, because it may just slide, the upper portion gone and only the lower 20 meter is left and the rest of the water is gone. So that kind of failure if taking place, then it's really critical and it should not happen. So the uplift pressure is because of the seeping water. Water seeps through the foundation, through the dam body, through the soil formation below, and it exerts pressure. Basically, it holds the weight on itself. Reaction, foundation gives the reaction. Rather, if there is seeping water, then it gives the reaction and holds the weight. So ultimately, the net effective weight reduces. That is what is the fundamental uplift pressure you need to understand. The provision, as I said, you need to go through while calculating the forces. The IS code 6512, that is 84, and there are many revisions of this to design and calculation of the forces. So this IS code you need to refer for calculation, and uplift pressure has been explained in detail for this pressure or force. I explained this through the sketches. I'll take the next here, that how the pressures are calculated. We have already seen, so I won't take much time on to this calculation. Only I would explain one thing which is important in the dams and how these sketches are created. Now this is dam section. Here we have considered a perfectly vertical surface, perfectly vertical surface of the dam. This is concrete, and this is the top road section, or you could say the freeboard here, and the downstream is slanting, and this almost a triangular, and on that there is a road kind of. And here a drainage gallery is shown. A drainage hole is created for the inspection of the work inside, and the seeping collect the seeping water through the dam. So drainage gallery, there are functions of drainage galleries, that seeping water is captured. It arrests the seeping water and then drain it outside downstream of the dam. So it basically, if you remove the seeping water, then you are reducing the uplift, and while reducing uplift, you are increasing the self weight of the gravity dam. If you are increasing self weight, then in turn stabilize the structure. So that is what is the important thing. Now the kind of thing that how to calculate the uplift pressure, in the previous section we have measured the water pressure being exerted on the dam section. Likewise, here is also gamma WH. H is the height of here the water held upstream. So gamma WH was the maximum at the bottom of the hydrostatic force acting onto the dam. That same ordinate is taken here, gamma WH, and onto this side. This is one way of calculating. The first trapezoidal sketch, if you could look at in my slide, then this the first sketch shows you the gamma WH, the one ordinate here. The second ordinate is gamma W small h. Small h is the water on the tail end. Here there is also water. Upstream there is water with capital H, and onto the tail end, the downstream of it, there is water. If there is a plunge pool, then there is water. If there is water released from the sluices, there is water on the downstream. If there is water released from the spillway, there is water onto the downstream. So if you consider downstream water depth as h, small h, then it will give ordinate as the gamma WH. So gamma WH. So we draw at the bottom, we take the whole width of the dam. This whole width, this represents this length represents the width of the base of the section, and we draw these two ordinates, and then we linearly connect and the cross sectional area and multiply by the unit weight of this water, and we get the uplift pressure. Now there are two more things here. If we provide drainage gallery here, then what happens? This gamma WH, this is the third figure I'm showing you here below the sketch, that this is gamma H, the same ordinate taken. This is a small h into gamma W. And if there is a drainage gallery, means we are removing the seeping water, then what happens that it reduces this ordinate where the drainage gallery is located. And how it is reduced, you could look at that. It is gamma WH in bracket H, capital H minus small h divided by 3. So this has been reduced because of drainage gallery. So you could say to reduce the uplift pressure, could we go for more than one drainage gallery? Then answer would be yes, but it should not reduce the total strength of the concrete. If you are constructing or providing too many galleries, say you are providing 10 galleries very near, so in that case the bonding of the concrete itself would reduce. So this is not advisable so generally one drainage gallery is provided. In few dams you will find more than 1, 2 and 3, up to 3 galleries. If you are going, it's okay to arrest the seeping water. Now the third, the middle diagram of the uplift is very interesting. Very interesting, you need to understand. This may be asked in many GPSC exams. If there is a concrete dam like this and there is a crack onto the upstream side. If there is a crack onto the upstream side, then how would you draw the uplift pressure diagram? In that case, the total base width, we take this width as the base width, but we do not go linearly reducing up to this here. We keep it if the length of the crack onto the heel of this here is B. This is B, might be visible to you, small b. So that is what is the length of the crack, and we have to go horizontally, means we are keeping that ordinate constant up till the crack length. So there is more of uplift, and many a times if the crack length is increasing, means your uplift is increasing. Uplift is increasing means your dam is becoming unstable. So this fails ultimately because of this reduced base width. Base width of the dam is very important. As per height, you will find that base is also almost 80% of the height. If height is say 50 meter, you will find that the base width of the dam is around 110 meter. So if there is a creek onto the keel side here towards the upstream, then it reduces the base width, effective base width. Effective means physically width is there, but because of that creek, it cannot be considered that providing strength to the structure. So this is one of the important structural consideration in structural consideration in calculation of the effective base width or length of the uplifted diagram. Now, these are three important forces which we have covered. One is the weight, which is there. Second is the hydrostatic force or the water pressure. And third is the uplift pressure. Now, we are switching over to the things which are lesser important, but they are important depending upon the dam where it is located and how it is being taken care of. Now, the fourth pressure we are considering is the silt or the earth pressure. When we are constructing a concrete dam, then what happens? We remove the top strata till we reach up to the hard strata. The kind of foundation we require to construct the gravity dam, we need a good impervious foundation. So the upper layers of the material should be scraped out. While scraping out, and then we construct the concrete dam. Then after construction, the material again dumped into the trenches which have been created earlier, but concreting is not done. Trenches are there all along the length of the dam. Then that is dumped. So that also a kind of a pressure exerted onto the dam section, but it is very negligible, can be ignored. If considered, then we can consider unit weight and calculate the total volume of such material and that thing. This is one important thing. The second important thing is that the silt which is taken by the erosion from the catchment, like we have been discussing, the Narmada's catchment is 1 lakh square kilometer, 90,000 square kilometer. So that big catchment, then water flows into the reservoir, and when it comes, it brings silt. And when silt is there, then the density of water does not remain the same as it is like 1000 kg per meter cube or 10 kilonewton per meter cube. So density changes, unit weight changes from that 10 kilonewton per to like 1360 kg per meter cube or 1925 kg per meter cube. The last bullet, the provision is done here that when there is silt in the water, the unit weight doesn't remain same as 1000, but it changes from 1360 to 1925 depending upon if it is horizontally exerting the pressure, we take it 1360. If it is vertically, then silt exert more pressure and we consider 1925 unit weight. Mind it. So I show you the sketch how it is being considered like this. When the coming water which is inflow into the reservoir and it gathers, accumulates silt into reservoir, then it reduces the active storage capacity of the reservoir. It reduces active storage capacity of the reservoir. I have mentioned that Krishna Raja Sagar is now running with only 10% active reservoir capacity. Earlier it was like 12,000 MCM of the Krishna Raja Sagar Dam in Visvesariya's area, that is near Mysore. Now here you look at, if silt has been occupied this much, then it is additionally exerting the pressure, means it is causing the failure, at the same time reducing the active capacity to store the water. And what we have to do here, this silt is up to dotted line. If you could if you could see this, my dotted line on the sketch on slide. So this dotted line is there. So this is what is the silt, and we have to calculate the additional silt pressure. This is not pure water. This pure water is there. So there is a kink in the hydrostatic pressure up to the pure water, which is not silt laden. We calculate it per 1000 kg per meter cube, and below this we calculate as 1360 kg per meter cube. And here also, if it is silt laden, we have to take care that we are multiplying by 1925 kg per meter cube. So that is what is the kind of thing we have to take care while there is silty water in the reservoir, or there is erosion in the catchment, sedimentation in the reservoir. So this is one of the very large topic of consideration: sedimentation of the reservoirs, dams, erosion of the area, wind erosion. You might have studied in 10th, 12th, wind erosion, soil, water erosion. So erosion is ultimately troubling our civil engineering infrastructure, that you need to note here. This ice pressure is not very critical in India, but in cold countries and in other areas where water is water temperature is dropping below zero, sub-zero temperature, then freezing and then melting of ice and again freezing could be hazardous. In Himalaya region, in high altitude areas, this is a kind of problem. Few dams are built in Tehri. It has been taken care of. I have shown you that highest dam is Tehri in India, which is partly the concrete, partly is the dumped material, earthen dam. And this need to be taken into consideration in case where water getting freezed in winter. So what is IS recommendation? That IS recommend that the area which is being subjected to ice pressure, which area? Top of the reservoir only freeze, not the whole water. The top, say, 2 meter of depth of water getting frozen during winter, or say 3 meter or 4 meter getting frozen, and the area which is in contact with this ice of the dam need to be taken. That area we calculate depending upon the experience of engineer or the other person working onto the dam, and then the pressure is taken as the ice pressure may be provided for at the rate of 250 kilopascal. What is Pascal? You write down this in what is Pascal? Write down in chat box. What is unit of Pascal? This 20 to 250 kilopascal. Anticipated area which I just mentioned. Nobody has mentioned yet. What is Pascal? It's the pressure unit. It's Newton per meter square, isn't it? You remember this? No? So that 250 kilo, here kilo, 1000 Newton per meter square. Pascal is very small unit. We don't bother about that. Okay, I need to cover in 10 minutes of time. The 5 minutes I will take more. So ice pressure is 250 kPa onto the anticipated area, which is contact. So that is IS code 6512, which I mentioned. You will find, and also you could look at 875. The wind pressure. Wind pressure is different than wave pressure. You all of you take a note of this, that there are two forces: one, wind pressure, and wave pressure. Wind, like we anticipate wind on our residential building, and you do calculation in your high-rise skyscrapers. Likewise, in the dam section, the downstream side is totally exposed to winds, because there is no water. So we need to consider if it is really troubling to the structure. Otherwise, not a major force and can be ignored. Even in IS code, it is written that it can be ignored if it is not severe. But if it is structure is important, then a separate study should be done whether it is important or not important. Ignored, could be ignored, or could not be ignored, like that. Okay. Thermal load, the temperature variation, I mentioned in the beginning that the morning temperature, noon temperature, evening temperature, night temperature, change in temperature, and the downstream side of the dam is exposed to sun radiation. So there are changes in the water temperature, there are changes in the concrete temperature. This differential temperature, cooling and heating causes stresses to be build up in the dam section, and basically we should not permit any temperature variation which allow the permissible concrete stresses go beyond the limits mentioned in your 456 FCK. You know, the permissible concrete stresses mentioned in the 456 IS code. So consider that any thermal stresses which are adding to the load, the pressure stresses from the other forces, here the thermal stresses should not add up, or at least it should not take it to beyond the permissible stresses in the concrete. I won't take it much because these are not that much significant, but we need to consider while constructing the dam, because there are temperature, hydration, heat of hydration. You might have heard in the second year of your civil engineering that heat of hydration in mass concreting is much. So need to be taken care of during the construction stage. Construction stage is not small, it's a 7-year, 5-year period. So you have to take care of that thermal load, temperature variation, heat of hydration, and there are cooling towers installed during the construction of Sardar Sarovar Dam. You won't believe, chilling plants were there onto this site. Nowadays they have been taken out because the construction is complete. But because of mass concreting, there was chilling and ice making plants established onto the site. So don't worry about the money. They are engineering requirements as per IS code. This wave pressure is important, but I explain, time is not there today with me. I explain in nutshell that wave pressure depends upon the shape of the reservoir and the extent backwater effect, कि कितना पीछे तक इसका असर आ रहा है, whether the reservoir is causing 50 meter backwater effect or 100 kilometer or 200 kilometer. In Sardar Sarovar it is up to 200 something kilometers. So wave generates, and it created a kind of like splash onto the dam section upstream. So that splash defined basically the top freeboard, as sometimes load is also considered. So this kind of formula is mentioned in the IS code, that very simple. This is a formula. Only two things are taken care of: fetch and the velocity of wave, which is can be taken as 120 kmph for the normal pool level and 80 kmph for the maximum pool level. And the fetch is like कितने किलोमीटर से वेव आ रही है, that is considered as fetch. तो लेस देन 32 किलोमीटर से आ रही है या 32 किलोमीटर से ज़्यादा से आ रही है, तो ये मोलिटस फॉर्मूला जो एम्पेरिकल नेचर का है बहुत ही ज़्यादा, तो ये हमें हाइट ऑफ द वेव देती है. हाइट ऑफ वेव से हम प्रेशर निकाल सकते हैं. ये जो लास्ट लिखा हुआ है ना आपका यहाँ पे PW, ये प्रेशर है 20 HW H स्क्वायर. बहुत सिंपल सा फॉर्मूला है वेव प्रेशर का कि 20 टाइम्स हाइट ऑफ द वेव का स्क्वायर, that is what is the pressure exerted the wave. But this is like 5-10% of the total loads we are calculating in many high dams. So we can't ignore it. We need to calculate the height of the wave, and it also describes the freeboard, say 3 meter or 4 meter or 5 meter or 1 meter is only sufficient.